mirror varies, and the variation simply depends on the position of the object. As we went through, we saw that there is only one position where a virtual image is obtained. All other positions, the image form is real. There is only one position of object where a virtual image is obtained. All other positions, image is real. What is that position of object which will give us a virtual image for concave or converging mirror? Can somebody share what is that position of object which would give us, or which will produce a virtual image for concave mirror? Anybody? Anybody to share that with us? We saw that a virtual image will be formed on only one position of object. What is that position? Free will. If you remember, just share with us. Free will. Over to you. Free will. If you remember, share that with us. What is that particular object position where the image will be virtual for concave mirror? Okay, Ohima.
The place one is formed behind the mirror.
Yes, a virtual image must be formed behind the mirror. Ohima, you are right. But the question is that yesterday's ray diagram, we saw that a virtual image will be formed by a concave mirror on account of only one position of the object. What is this position which will form a virtual? Go ahead.
Sir, please, when the object is between the focal point and the pole.
Good. Thank you. So, for a quick identification, let's sketch that. For deepening of concepts, let's quickly sketch that. Don't forget, we rule the vertical line behind it in order to cater for reflections that go beyond the aperture of the mirror. So if this is the pole, you measure your focal length. Don't forget R is equal to 2F. So if my focal length is X centimeter, my radius of curvature must be 2 times X. In numerical terms, if I'm choosing 5 centimeter, then the radius of curvature must be 10. So if we place the objects between the pole and F, what will be the nature of the image? Placing the object between the pole and F does not necessarily mean that place it at the center. Any position between F and P is okay. So let's use our rules. Any two of them, a ray which is parallel to the principal axis. After reflection, the reflected ray must pass through F. A ray from the object hitting the mirror at 90 after reflection must pass through C. All other rules can also be used. So this is incident. Rays must be shown using arrows. So reflected, incident, and reflected. If you look at the two reflected rays, it is obvious there is no way they will meet in front here to form real image. So let's extend the reflected rays backward to see if they can possibly meet. So when we extend this and we extend this, when you are doing this, because you will be taking, using a ruler, a straight edge, this must be a broken line. The projected image at the back or lines at the back must be a broken line because it's a virtual thing. It doesn't really occur, but it appears to be happening. The head of the image is determined by an arrow. The foot is on the principal axis. So this is the image. Okay, let's quickly discuss this image form. One, image is virtual. Image, Francisca, mute yourself. Image form is virtual. All virtual images are erect or upright. Francisca, mute yourself.
Yes, sir.
Image is upright or erect. 3. Image is magnified. When you look at image size and object size, the image is larger than the objects. Oh, so image is magnified. And finally, image is formed behind the mirror. So these are the characteristics of the image formed when object is between the pole and the principal focus or the focal point. I hope that's understood. If you have any question to ask, quickly do that. Then we have two key positions to look at. What will be the nature of the image when object is at F? When object is placed at the principal focus, how would the image look like? And when image is at infinity, object is at infinity, what will also be the nature of the image. Let me quickly drop attendance, okay, and then get back to just a minute to take attendance, and we continue. Ray diagrams must be very neat. So when you are doing ray diagrams, use pencil, eraser, and straight edge. You lose huge marks if it is dirty. Your ray diagram is not nice. And sharpen your pencil very well. Evelyn, have you fixed your microphone issue today? Once there is no feedback from Evelyn, it means the problem still lingers. Okay. Okay, so back to you. So if the object is at F, what will be the nature of the image form? So to show that this is concave, the lines, I can decide to ignore my vertical line, knowing what to expect. I can do that. So measure the focal length. Values are not given, so you must estimate, but make sure that you take measurement. The focal length must be equal to half of the radius of curvature. So this is C. Now, object is at F. So place the object at the focal point. Good. Then we use ray diagrams, just as in our rules. So a ray of light parallel to the principal axis after reflection must pass through F. Must reflect and pass through F. A ray of light hitting the mirror at 90 must reflect and pass through C. Here, the only rule which can't be used is a ray passing through F. This is because the object is at F, so you cannot use that rule, but all other two rules can be used here. Incident reflected. Now, if your measurement is done very well, what you realize is that the two reflected rays will be going in that parallel manner. Mine is not absolute. The two reflected rays are not directly or accurately moving in that manner because I did not measure and I don't have what it takes to take measurements. But when you use straight edge, you realize that no matter how you extend these two lines, they will be going in that parallel manner. No matter how you extend them. Let me try extending mine a little bit. And it's even the same. So no matter how you extend your lines, they will be going in that parallel manner. They traveling in that parallel manner is what we conclude. Based on that, we make the conclusion that image is formed at infinity. Image is formed at infinity. So why do we say that image is formed at infinity? Because the reflected rays are traveling in that parallel manner. So if you are asked why the image is formed at infinity, it is just because the reflected rays are moving in that parallel manner. So let's discuss the characteristics of the image that will be formed at infinity, or the nature of this image, nature of the image formed. One, image is formed at infinity. And infinity is a far place. We can't precisely tell where exactly is infinity, but all that we know is that it's an infinite place. Two, image formed is real. I will explain why it is real. Image is inverted because all real images are inverted. And four, image is magnified. These are the four characteristics of the image formed when object is at infinity. Do we have any question to ask? Feel free to ask any question on your mind, and I'll explain. Class, feel free to ask your question. Ohima, Jude, Lamb, Hayfron, Paula, Mackenzie, and all of you. Do you have any question? If you don't ask the question, I'll ask you. So you better ask now. Hayfron, are you there? Okay, so if you do not have question to ask, my question to the class is, how do I know that the image is real, inverted, and magnified? How do we know that the image will be real? I've explained to you why it will be formed at infinity. But how do we know that the image formed at infinity will be real and even magnified? Yes. Ohima. Ohima. Ohima, I can hear you.
Sir.
You didn't ask. So how do we know that the image will be real and magnified?
Sir, please, I don't know.
Okay. Yeah.
Sir.
How do we know that the image will be real and will be magnified?
Sir, please, I don't know.
The simple answer. Okay. Then I have to answer. All right. Now, he said all real images are inverted. Infinity is an infinite position, very far place, which we don't know. So let's even suppose that infinity is at this point over here. We are assuming if infinity is here, then we expect the two reflected rays to converge at this point. We expect these two reflected rays to meet here. If that point is infinity, it's an assumption. We are assuming. So if that point is infinity, then the image, I said the foot of the image and the object is always on the principal axis. So if we are to draw the image, this is how the image will look like. Where they are meeting is the head of the image. So it means that the image is here. And is this image upright or inverted? Class, is it upright or inverted?
Inverted, sir.
And once it is inverted, then it means the image is real. Because all real images are inverted. Okay. 2, how do we know that it is magnified? Look at the object. the size of the object and the size of this image. The image size is far greater than the object size. So the image is magnified. So it is of this reason that we've got the characteristics of the image when object is at the principal focus F. Class, let me quickly update the attendance whilst you draw. So if somebody asks you to explain why those observations, these are the reasons or the characteristics. Okay, so back to you. Now, if the object is at infinity, how do we draw a ray diagram to form the image? Can I flip to the next page? Class, can I move to the next page? Yes or no?
Yes, sir.
Okay. So, object at infinity. Here, light obeys the principle of reversibility. The reversibility of light. Simply what it means is that if light is moving from A to B, when it's moved from B to A, it must give you almost the same characteristics. So we place the object at F and saw that the image will be formed at infinity. Through the principle of reversibility of light, if the object is to be placed at infinity, the image will be formed at F as well. But how do we use ray diagram to do this? That's the key issue. By the principle of reversibility of light, we know that the image will be formed at F. But how do we show? So let's take our measurement. P is here. Let's measure F I'm stressing on the fact that R is equal to 2 times F. So if X centimeter for focal length, then 2X for radius of curvature. You are to take measurement. Okay. Now, when reflected rays are going to infinity, they go in that parallel manner. So reflected rays incidenting at infinity must be parallel. Conversely, incident rays from infinity must also be parallel. I said they all obey the law or the principle of reversibility. So if reflected rays, if image is being formed at infinity, then the reflected rays must travel in that parallel manner. If an object is at infinity, then rays coming from the object must also be traveling in that parallel manner. Okay. Class, are you okay? Are we listening?
Yes, sir.
Yes, please, sir.
And this must happen because of the principle of reversibility. So to show that the object is at infinity, rays coming to the mirror must come in that parallel manner. Okay, so this is how we do that. A ray of light which is passing through this, a ray of light which is passing through the focal point from wherever the object is. Oh, hold on. Hold on, I'm coming. So let's start with this. A ray of light hitting the pole must reflect at the same axis. It must reflect at the same axis. So this angle here must be the same as and here you must take your measurement very well. So I'm coming. To get things right, I'm coming. Let me estimate this angle to look like. So when you are doing this, please, you can use protractor to take measurement. Something like this. Then a ray of light from the object, which also passes through F, must be parallel to the other ray. must be parallel to this. And once the ray is passing through F, after reflection, the reflected ray must be parallel to the principal axis. So if you take your measurements right, look at where the two reflected rays, there's the incident. There's the incident. Look at the reflected. There's the reflected. This is also the reflected. If you take your measurements right, you observe that the two reflected rays will converge at, will meet at F. And once the two reflected rays converge at F, it means the image will be formed at F. Per my diagram, my measurement isn't correct. That is why the two rays are not meeting at. So I'll draw again. And then this time, look at my estimated length. So that's why I'm saying that when you are doing this, use measurements, take measurements. Because if you don't measure well, it will affect the position of your image. So I'm estimating F well. But you can have that so easily because you will be using okay, so I want to estimate this very well to get it accurately as possible this time around. So C is here. So once object is at infinity, the lines coming to the mirror must come in that parallel manner. I want to vary my rules. That's why I'm rolling the line there. So a ray of light hitting the mirror at 90 must pass through C. So simply, it means that this is hitting the mirror at 90. Then a ray of light passing through F must be parallel to the other ray. And once it's parallel, the reflected ray this is also far away. So as I said, that's the issue when you don't take measurements. So ideally, I expect these two rays to intersect at a position F. So this is even close The first one is closer than the second one. So let's take the first one. But as I said, if you take your measurement, you will see it. You get the ray, the image formed at F precisely. Okay. So this is the indication that the object is at infinity. Why? Because the rays are coming in that parallel manner. Okay. Now let's describe the nature of the image formed. The nature of the image formed. 1. Image is formed at F. Is formed at F. At F. 2. Yes, help me describe the nature of the image formed. Image is formed at F. Yes, class, I'm waiting for you. Look at the image and then let's discuss it. Yes, David. Image is formed at F. What are the other characteristics? Is the image real, virtual? I spoke about this quietness in class. Share your views. Yes, yeah.
Sir, please, image.
Yeah, your line is fading.
Sir, please, image is inverted.
Good. If it's inverted, what does it mean? Yeah, go ahead.
It is real.
Image is real and inverted. Yes. Any more observations? Yeah, you again. Yeah, go ahead. Lamp. Tell us what you have also seen. Lamp. Lamp. Tell us what you have seen. We are discussing the nature of the image form or the characteristics. Ohima. Evelyn, the rays emerging from the mirror say are parallel. No, they are not. If they are parallel, they will not intersect. Okay, once they are intersecting, then it means they are not parallel. Look at the object size and then the image size. And in estimating the object size, let's assume infinity is just here. This is infinity. So if infinity is here, exactly. Ohima.
Sir, please, you have said
I've said what?
the image is magnified.
Okay. So supposing the Infinity is just here. Look at the size of the object. And then compare it to the size of the image. So what will you say about the image? Ahima, what will you say about the size, or how would you describe the image?
Sir, please, the image is diminished.
Good. So image is diminished. So that's all. That is all. They are not so difficult, but you must understand how it works out. If object is at infinity, then the ray coming to the mirror must come in that parallel manner. And when you take your measurements correctly, the reflected rays would intersect at F to show you that image will be formed at F. And if the image is formed at infinity, the reflected rays must also go in that parallel form. Is there any question? Class, is there any question? Okay. So that is it with ray diagram. So I want you to using ray diagram state the characteristics of the image formed when one object is placed between C and F. So start work. I'm giving you 5 minutes or 6 minutes to draw. Use ray diagrams. If you're asked to use ray diagrams, we expect you to draw as I've done. Okay, when you finish, use the rules. When you finish, you then list the characteristics of the nature of the image formed. Meaning you extract your characteristics or nature of the image from the ray diagram, just as I've done. So start work. Object must be between C and F. So use ray diagram to describe the nature of the image form. Start work. 6 minutes, after which we'll discuss. Okay. All right, I'm waiting for you. My time is 6:57. So at exactly 7:03, I'll come your way. Please, each one of you must get involved. If there is a need for inquiring from a friend, you can do so, discuss. Okay, 6 minutes. You have 3 minutes to go. 3 minutes more. Two minutes. Your time is up. So let's discuss it. So as we discuss, you will be marking whatever you've done. Okay, so object is between C and F. Any position between C and F will do. So let's use the rules. A ray of light, the rays must always come from the object, parallel to the principal axis after reflection, must reflect and pass through F. A ray of light which is through F must reflect, and the reflected ray must be parallel to the principal axis. So we look at the point of intersection of two reflected rays. This is where the two rays are intersecting. So that is where the head of the hello. Good. So this is the head. So this is the image I, the object O. By this, we could deduce that one, image is real. Image is inverted. Image is formed beyond C. And image is magnified. These are the characteristics of the image form. Show by hands, those of you who scored everything. If you got everything correct, please show by hands. If you got all the ray diagram correct, and then the characteristics, Hefron got it. Who else? Then Kezia Santi also got it. More loyal hands. Then Ohima also got it. Is that all? Okay. So if you didn't get it, please, this is how to go about it, okay? This is not difficult, so you master and then. All right. For convex mirror, yesterday we saw that no matter where you place the object, the nature of the image form would always be the same. You can. So for convex mirror, we don't discuss different positions. We don't discuss different positions. But no matter where you place it, the nature of the image form will be the same. In case you were not here yesterday, I'll just sketch one or two different positions, okay, to help you. Then we move on. So for concave, convex mirror, curves, the reflecting surface curves outwardly. This is the pole. For convex mirror, the principal focus and then the center of curvature are all virtual. So they occur at the back of the mirror. So F is here. Take this one, you must take your measurements. C is here. So let me extend the principal axis so we can place the objects on it. Object is always in front of the mirror. So we want to bring the object closer to the mirror. Oh, object. So use our rules. A ray of light parallel to the principal axis after reflection will diverge. This one diverges rays, but the diverted ray always appears to be diverted from a point behind the mirror, and that is F. Now this point is really actually a virtual point. It doesn't actually happen. And so we most often indicate it with broken lines, not a solid line. Then a ray of light hitting the pole the rays are always from the object. A ray of light hitting the pole must reflect at the same axis. So this angle here must be equal to whatever I'm coming to draw as an angle. And I am estimating. You can use protractor to get the exact angle. Now look at the two reflected rays. This one and this one. They are becoming widened the more. So there's no way they would ever meet to give you real image in front of the mirror. Okay, so just as we did when the object, for concave mirror, when the object was at between F and P, we extend the reflected rays back where they appear to meet becomes the position for, and it's a virtual thing. That's why I'm also using broken line for this. So, but when you must use straight edge to draw the broken line, this is where they appear to be meeting. So the image would be here. But this is the image I. Okay. Now image is virtual. all virtual images are erect or upright. Image is diminished. Meaning the image is smaller in size than the object. An image is formed behind the mirror. I want you to take note of one thing. The image is formed, though it's behind the mirror, but it's formed between the pole and F. Okay, it is restricted between the pole and F. And that is the general position for all positions of the object. So I'm going to also take the objects far. Here, the object is close to the mirror. I'm going to take it a bit far and still use ray diagram too. So F is here. And then C is here. I must extend the principal axis so that I can place my object. So the object is here. The head is here. So using ray diagrams, let's form this. A ray of light parallel to the principal axis would reflect, and the reflected ray will appear to be reflected from F. So this will be the reflected ray. So incident, this is a reflected. Then a ray of light from the object which is hitting the mirror at 90 would appear to be passing through this. I'm varying the rule. So the moment you see the ray passing through C or appearing to pass through C, then it means the ray is hitting the mirror at 90. Please, this is a virtual thing, okay? But because I cannot break it into use broken line, that is it. So look at these two reflected, this one, and this one, and this one. In front of the mirror, they are getting more diverted. So we We look at where they appear to meet behind the mirror, and there's it. They appear to meet behind the mirror at that location. That is where the image will be formed. So, still the image is real, virtual and upright. Image is real, image is upright. Image is diminished, formed behind the mirror, but its exact location is that it is formed between P and F. Okay, so no matter the object position, the image is always closer between P and F, and the image form is always closer to the mirror, no matter the object's position. All right, and yesterday I told you that it is of this reason that there is this writing on convex mirrors or divergent mirrors that objects seen in the mirror is closer than they actually are. So meaning that when you watch through the mirror, the images you see, which are the objects they are referring to, are always closer to the mirror than the real objects. Okay, so that is the reason why. So you can be asked to explain why convex mirrors have this writing that object seen in the mirror is always closer than they actually are. It is because in convex mirrors, images formed no matter the object position is closer to the mirror, That is it. Now this most often helps in reverse driving. It helps in reverse driving, meaning that if you are driving and you are moving backward, you have to watch through the side mirror or the head view mirror. As you look through, whatever you see as the image or object in the mirror is always closer, okay, than they actually are, than the position of the object itself. So as you walk through the mirror, when you feel like so close to the person and you are hitting it, in reality, you are not yet close to the object, but it will help you because you are looking through the mirror. It will help you to quickly apply the brakes and stop to prevent hitting the object. But in reality, you are not there yet, but the mirror is giving you that optical illusion that you are there. All right. Hello, all right. Is that clear? Class, are you okay?
Yes, sir.
Yes, sir.
All right. Sir. Let's look at defects of the mirror. Defects of the mirror. Mirror has its own defect. Problems. Defects of the spherical mirror. Concave mirror, for instance, is used as reflector in torchlights. It's used as a reflector in torchlights and car headlight lamps. Now, concave mirrors have problem or defects. The defect is that when you incident parallel beam onto concave mirrors, all the parallel beam would converge at the focal point or the principal focus on condition. It's not all the time, but on condition. What is this condition? If the rays are close, very close, and parallel to the principal axis. So I'm drawing several rays that are close and parallel to the principal axis. So these are rays that are close and parallel to the principal axis. Once they are all close and parallel, they will reflect and all of them will converge at an exact location on the principal axis. So this is F. Now what happens when the rays, and please, rays that are close and parallel to rays that are close and parallel to the principal axis are called para-axial rays. Para-axial rays. So para-axial rays are rays that are always close and parallel to the principal axis. So if we have para-axial rays incidenting on the mirror, they will all converge at a common point after reflection. What then happens if the ray is not so close and parallel to the principal axis? If the ray is not paraaxial enough, it creates a problem. And this is what we are calling as defects. So these are rays that are not close. One, they are parallel to the principal axis, but they are not so close to it. If the rays are not so close to the principal axis, what happens is that after reflection, they will converge at a different location. Meaning they will create their own principal focus. So we have another principal foci. We have F1 and F2. These rays, which are not close, far away from the principal axis, are also given a special name. They are known as marginal rays. Rays that are parallel but not so close to the principal axis are known as marginal rays. So marginal rays are parallel, all right, but they are not so close to the principal axis. And as such, when they incident on the mirror, it creates another principal focus. So if we have some rays very far and some rays very close, it creates double or two principal foci. This defect where double principal foci are formed due to marginal rays is called or is known as spherical aberration. aberration. So spherical aberration is a key defect of mirrors. Okay. Now, when spherical aberration occurs, what happens? The convergence of the reflected rays must give us real image of whatever is producing the incident rays. Now, when you have spherical aberration, the image formed is blurry. So spherical aberration creates double image or double images that are blurry and indistinct. Indistinct means not clear. That is also the reason why usually some images will be seen as like ghost images. It is not clear, looks like ghosts. So when the image looks like ghosts, that is what we term as blurry image. Blurry. Class, are we okay?
Yes, sir.
So when it will create double image because the paraxial rays are forming an image, so is the marginal ray. So double image is created, which is not so clear, looks like ghosts, just as the defects of concave mirrors, known as spherical aberration. Known as what? Spherical aberration. So in mirrors, how is spherical aberration eliminated? Are you done writing? I want to flip to another page.
No, sir.
All right, then hurry up. So how is spherical aberration of concave mirror eliminated? When you finish, please let me know. So stage one effect of a concave or mirror, spherical mirror. Please here, it's about spherical mirrors, not plane. That is spherical aberration.
Sir, please, I'm done.
Okay. So how do we eliminate spherical aberration? To eliminate or to reduce or reduce spherical aberration instead of using a concave mirror like this, the shape is changed. Instead of using concave, the shape is changed to a parabolic shape. So instead of this shape, we use this. Let me redesign it again. So instead of a concave shape like this, the shape of the mirror is like this. So it is shaped like this. And this shape is known as parabolic shape of mirrors. And you see this in most car headlight lamps and torchlight reflectors. So instead of a concave shape like this, it is shaped in that parabolic. So look at car headlights and then torchlight. That reflector, that shiny thing in torchlight. You will not see this, but it's been shaped like this. The reason is that when you shape it in that parabolic manner, no matter the position of the incident ray, whether so far from the principal axis, let me draw a principal axis. So if you shape it in this manner, no matter where the ray is coming from, whether marginal or paraaxial, it will still reflect it to that same point. We wouldn't have a situation where we'll have two principal focus. So when it is shaped, all reflected rays will still converge at a common point. No matter whether it is marginal or axial, you have a common principal focus for all of them. So here you have one. So this is how spherical aberration is eliminated in spherical mirrors. In concave mirrors, please. This defect pertains to concave mirrors because they are the only kind of mirror which is used as a reflector in cars and then torchlights. So this is how we eliminate spherical aberration in concave mirror. Class, are you okay? Are we okay?
Yes, sir.
All right. So the next thing we must look at is mirror formula or mirror equation. The mirror formula or equation. The mirror formula or equation is actually given as 1 over F is equal to 1 over U plus 1 over V. We will prove it. We will derive this where F is equal to the focal length of the mirror. U is equal to the object distance. V is equal to the image distance. We'll go through this next week. But why the mirror formula? We have this because apart from using ray diagram to describe the nature of image form, we can also use this formula to describe the nature of the image form. Okay. So we can also use the mirror formula or equation to describe nature of image form depending on values we have for image distance, F, and all that. Okay. So we define the mirror formula as a mathematical equation, equation or relation that expresses the relationship between object distance U, image distance V, and the focal length F of the mirror. So it's a mathematical equation or relation that expresses the relationship between object distance U, image distance V, and the focal length F of the mirror or of a mirror. The mirror formula is applicable to all kinds of spherical mirror. The mirror formula is applied to all the category of curved / spherical mirrors, meaning that it can be applied to concave, both concave and convex mirror or mirrors, meaning it can be applied to both concave and convex mirrors. Don't forget, it is not applicable to plane mirror. A plane mirror is not a curved mirror. Okay. So next week, we'll go through spherical mirrors. Look at how this formula is obtained. How we obtained the formula 1 over F is equal to 1 over U plus 1 over V. I'm sure this equation is familiar to you. Class, is it familiar?
Yes, please.
Where have you used this equation before? Where? Under which subjects? And under which topic did you use this?
So come at change of subject.
Exactly. So GHS, you were given this and then being told to make one of the letters the subject. Okay. Yes, it is the bona fide property of we versus people. So it is not for the mass people, but us. So we will prove how this formula actually came by, and then look at how it is used in solving problems also next week. Please, if you have any question, quickly ask. Is there any question? Are you done writing? Are you done? Okay,
Yes, sir.
so it is also an alternate way. The mirror formula is another means by which nature of image formed, by which the nature of image formed by spherical mirrors can be described. Okay. So another way of describing the nature of image formed in a curved mirror without, aside the ray diagrams. Okay. All right. So we have barely 4 minutes to end. This is where we'll end today's show. From next week, we'll look at the mirror formula, wash our hands of it. Then we look at refraction of light as well. All right. So This is where we drop the curtains on today's meeting. I'll use, as usual, upload the video. Please, when you watch the video, can you please subscribe to my channel for me and then share? Okay, subscribe and share so that I have to increase the subscription base and then the viewership. So help me do that. Okay.
Okay.
All right. So good night to all of you. I'll forward an assignment to you so that, let me see, so that it engages you within the week. All right. Once you have exhausted your questions, good night and bye-bye to all of you. I just want to, okay. Okay.